So thank you, everyone. Today, we've got 3 of our student awardees within the center who are going to be presenting their work. Since we've only got about 12 to 15 minutes per presenter, I'm going to be terse on the introduction. So first up, we have Melina Zaharias, who is going to be talking to us about some of her work on simulating the flow of hydrogen in the tiger stripes of Enceladus.
Hi, everybody. I'm Melina. Thank you for coming today and for inviting me to talk. It is an honor. It wouldn't be possible to have been able to do all this research without CPSH, as well as NASA and the Computational Fluid Physics Lab. So the Cassini-Huygens mission launched in 1997, and it was tasked to explore Saturn and its moons. It was initially noticed that there are these 4 main fractures stretching across the south polar terrain of Enceladus, and through these there are these gas plumes erupting water vapor, and recently found in 2018 hydrogen as well. And so this told us that there is likely a subsurface ocean, a reservoir, deep beneath the icy crust of Enceladus. So here we have a picture of some crevasses, I believe in Alaska, and we see that they span a few inches to a few feet. And on the bottom, we see the crevasses on Enceladus. However, these are spanning a few kilometers. So similar concept, but very different scales. This is a graphic from a paper written by Dr. Waite in 2018, which initially told us or discovered the presence of hydrogen on Enceladus. I would love to take the time to sit and talk about all of the information that this actually does give us. However, main takeaways is that the ion neutral mass spectrometer was in its open source neutral beaming mode when it detected these odd narrow spikes of hydrogen concentration. And so the biggest question was, how is this physical and where is the hydrogen coming from? So that leads us to, there are many possibilities or hypotheses as to what's actually happening, but the most likely case is that there are hydrothermal events on Enceladus. So similar to black smoker events, this image is from a black smoker in the Atlantic Ocean. And so it's very possible that there are black smokers or some sort of hydrothermal events at the bottom of Enceladus's ocean, which then bubble up and allow for hydrogen to be, I'm not sure if you'll be able to see this, and the ice conduits that we can barely see there. So there are 3 main thoughts as to what these conduits could be looking like. The first is a subsurface reservoir where the ice, gas, and water exist in equilibrium at triple point conditions with a boiling liquid gas interface, and the gas is able to trickle up through likely a converging diverging nozzle and eventually reach the surface and all gas as a plume as Cassini detected. The second is tidal pumping, where the ocean water seeps into these fractures, and as the ice contracts and releases, it raises and lowers the water level, causing a turbulent pump that could carry the energy from the surface of the water to the surface of Enceladus. And lastly, the possibility of a misty ice cavern. It's very similar to the reservoir. However, it's just a different physical makeup of the ice. So there are various vent geometries that have been explored via DSMC and other coding techniques. However, the difficulty with that is that we don't know the subsurface conditions of Enceladus. We are only able to detect the surface and above. So kind of guessing as to what the gas interaction with the walls is, if there's friction creating an imbalance of the back pressure, if water vapor is able to sublimate or condense with the ice wall, as well as the thermal anomalies that were detected near the tiger stripes that measured to be significantly warmer than initially expected. So to add to what's been discovered about Cassini, my goal is to characterize the interactions between water vapor and molecular hydrogen as it travels through the icy core of Enceladus. So I essentially conduct a sensitivity study varying 4 main parameters, being the inflow mixture speed, our inflow mass fraction, aspect ratio, and our icy wall temperature profile, and essentially look at how each of these parameters affect the flow pattern. So to kind of get a closer look of our nominal case and where I simulate, so we fall into the misty ice cavern reservoir assumption. However, we don't focus on the specifics of what's taking place. All we assume is that the ice, gas, and water are in equilibrium. There's some sort of naturally created converging, diverging nozzle within the ice that allows the gas to reach supersonic speeds. So in our nominal case, our domain size is axisymmetric and is 20 meters in length and 2 meters in radius. And we use a gas makeup of 99% hydrogen to 1%, or 99% water vapor to 1% hydrogen by mass. So this is an animation of our nominal case. Again, our inflow speed is Mach 2. So we see a shock formation start up and then it trickles into a steady state flow. Our mass mixing ratio in this is 99 to 1 by mass of water vapor to hydrogen. And our wall temperature profile is 230 kelvins constant. So this brings us to our first set of results. Here we vary our inflow gas speed, and to give a better understanding of what we're looking at, these are 3 different cases. And in the left-hand side, we see our hydrogen density, and on the right-hand side, we see our water vapor density, and they correspond to the same color bar that's next to each one. So as the bottom of our conduit is all inflow and the top is all vacuum, we see these little decreases in density at the top of our conduits, and that is just due to the boundary conditions, nothing to necessarily pay attention to. But when we actually look at what this is telling us, we see that in our nominal case, we have a normal shock at the inlet and it trickles into a fairly uniform flow. And in case 2, we have a sonic inflow. There's no shock structures, fairly uniform flow. However, when we look at case 3, where we have a Mach 5 inflow, we see a strong oblique shock that kind of ricochets throughout the whole conduit. And something that is very interesting about this is that we see an increase of both hydrogen and water vapor density in the center of our conduits here. And so I want to point back to when I was showing the initial data that was detected, and we were kind of asking, how is this physical? This gives one simple explanation as to how it could be possible that there are these narrow beams of hydrogen being outgassed. The next parameter that we're going to consider is our inflow gas mixture. So again, we have our nominal case on our left-hand side, and we compare it to a case of only water vapor. And we see that the addition of just 1% hydrogen by mass increases our wall pressure by 20%, which is a phenomenal result and could also help to explain as to why these icy conduits are not closing off. Next, we consider our aspect ratio, and it's worth noting that while these are visually the same aspect ratio, if we look at our axes, we have our nominal case on the far left, which is 20 meters in length, 2 meters in radius. And the center, we have 20 meters in length and 1 meter in radius. And then on our right-hand side, we increase our length to 40 meters and 1 meter in radius. So again, we see fairly uniform flow in our nominal case and in case 5. However, when we extend the length of our conduit to 40 meters, we see this increase in hydrogen density sort of in the center of the conduit here. And this is essentially due to a backflow. The hydrogen is not traveling at as fast of a speed, and so it kind of collects in the center, but continues to outflow beyond, just due to an ever inflow boundary condition at the bottom. And lastly, we vary our wall temperature. So here we see 4 cases where our nominal case, our wall temperature is 230 kelvins constant. In case 7, we have 230 kelvins at the bottom of our conduit, and it cools to 210 kelvins at the top. In case 8, we have sort of the opposite, where it's 210 kelvins at the bottom and warms to 230 kelvins at the top. And in case 9, we have 210 kelvins constant. So what is most interesting about these cases is that wherever the wall temperature is colder, we see this blanketing effect of hydrogen. This is due to sublimation being a function of our wall temperature. So whenever our wall temperature is colder, there's much less sublimation taking place, and the water vapor is just wanting to condense against the wall. So as it's traveling towards the wall, it's dragging the hydrogen along with it, which causes the hydrogen to kind of be continuously batted against the wall, and it forms this blanket of hydrogen that eventually prevents the water vapor from further condensing. And again, to kind of point back to our question of how are these narrow beams of hydrogen physical, this also helps to sort of explain that as if our wall temperatures are colder near the top, the hydrogen has the possibility to be outgassed at the sheet, or in case 8, where we see a colder temperature at the bottom and warmer near the top, we see the sublimation effect causes the hydrogen to be bent towards the center of the conduit, which causes a potential for a beam of an outgas of hydrogen. So that brings us to our conclusions. We saw that the presence of just 1% of hydrogen altered our wall pressure by 20%, and we saw that our temperature profile of the icy wall had the largest effect on our flow pattern. However, all of the parameters that we tested did prove to affect our flow. And going forward, it would be interesting to expand the flow beyond the surface and look at if these beams are holding true or if it just becomes uniform again. And also consider the presence of a jet-jet interaction, which could also cause strong beams of hydrogen. So with that, thank you for your time and listening to my talk. I'll take any questions.
I'll monitor the chat in case there are any there, but are there any questions from the room?
So I was wondering, which of these parameters do you think would be most sensitive to figuring out what the source of region is? Because it's kind of debated whether the plume is actually sourced from the ocean or if it's sourced from the ice shelf. So of these different parameters and your kind of results so far, which of these parameters do you think would be most indicative of where it's being sourced from?
That is a great question. I don't know if any of these specific parameters can point us as to like what specifically is the source, as that's something in our assumptions that we kind of gloss over. We just have this uniform mixture of gas in the bottom of our reservoir and simulate that. So we more so look at, I guess, the gas interactions than anything else.
Looks like you got one check.
Yep, I know. Yeah, so great talk. Is the DSMC code you utilize public, or is it fairly tailored for this type of problem?
It is fairly tailored to this type of problem. It's an in-house Planet DSMC code that our group specifically has been using for a few years.
We do make it available, but we don't necessarily support it night and day.
Understood. Another question from online. I wonder about the effect of surrounding wall roughness on nuclear shocks. Great talk. Judges, points through out to the head.
Thank you. Also a great question and something that we are interested in adding into our simulation, because that definitely would have an effect of especially the blanketing of hydrogen against the wall, if that still holds with a rougher surface.
I was wondering, I actually thought that the melt was created by friction on the walls. At least, have you come across that?
Say it again.
I thought that the one hypothesis for how the melt is generated was actually that this tidal walking on the fractures, and it melts, and then that melts essentially gets just sucked up. Have you come across that?
Have come across that, especially in literature. However, I guess the basis of this project is it being outgassed from the ocean. Yeah.
And so my other question was, you were talking about sublimation on and off the wall. So is the wall actually moving, or is your domain fixed?
No. So the wall is fixed, and if a particle sublimates, then it's created at that point.
Okay, so you just add it.
Yeah.
Okay.
All right, thank you very much.
Thank you.
Chair, then you should be able to share. I think that.
There's one more.
There's one more question if you want to answer it while you're switching.
Sure. While switching out, is it only the aspect ratio that matters, or are the absolute dimensions important as well? But if the vertical dimension is scaled up from 20 to 40 meters up to multiple kilometers.
I guess we were able to see a large change in the flow when we increased our aspect ratio to just 40 meters in length. So the aspect ratio would definitely affect our flow and what we're looking at.
Maybe along the same line, do you think you could just non-dimensionalize, right? It's just your results rather than varying, diameter and length separately.
Short answer is no.
Okay, well, that's
That was fitted.
All right, so next up we have Chun-Yi Wu, also from the Department of Aerospace Engineering and Engineering Mechanics, who's going to give us a little bit more on the mission design side.
Well, thank you for coming to the talk. Yeah, so my talk is going to be about the planetary moon tour trajectory design and planning. Before that, I want to just quickly acknowledge the funding was from the Applied Physics Laboratory from Johns Hopkins University and NASA, and I'm also very grateful for the funding from the CPSH for being able to finish this project. So a little bit of background. As Melina mentioned before, there's a lot of interest in the planetary moon missions. We have the oceans on Enceladus, Titan, and Europa, and there's also volcanoes on Io. But in order to send a mission to those bodies, if we do a direct transfer, the delta V will be so really large that it will be physically infeasible. So what typically is done is that we do long duration and high energy flyby tours. That's kind of on the order of like few years, 50 flybys, and going around the planet for like 250 revolutions. So it's a very complicated trajectory. And because of that, the design process is very lengthy, and that means it's very hard to iterate on that design, and therefore usually it's a suboptimal solutions. And so our goal here is to develop a set of tools that can facilitate the design by performing low fidelity broad search, optimizing the trajectory in the high fidelity, and having some intermediate steps that allows us to more easily converge the solution in the high fidelity. So first I'm going to talk about the Scout, our low fidelity post flyby reachability algorithm. It allows the exhaustive exploration of all the possible trajectories out to all reachable bodies with a pre-flyby V-infinity vector. It includes NPi transfers and V-infinity leveraging maneuver transfers, which are these trajectory that helps with more efficiently changing the orbit and the energy of the spacecraft through the use of flybys and maneuvers. Scout uses filters and ballistic solution finders to limit the search to low delta V transfers, and it provides interpolatable families of solutions that allows the design process to have bigger degrees of freedom to work with. So these are the inputs for the Scout. You have the initial condition, the time, which body you're flying out of, and the V-infinity vector. You have the information about the system you're traveling in, so the center body and all the flyby bodies, which is the moons. You have the search parameters that allows you to limit the search. The outputs, there are 7 categories of trajectories. There are the built families that either go to the same body or different body. The same body is also split into near resonant orbit or near non-resonant orbit. There is also the NPi transfer, including the half rep and full rep. All these return the arrival V-infinity vector, the final time, and the arrival body, which, as you saw before, is the same as the input, so it can get feedback right back into the algorithm. So here are the classifications for the output. I will not go into detail in interest of time. For the algorithm, in general speaking, we have these sub-algorithms. So we have the initial condition that we use the flyby analysis to figure out all the outgoing possible trajectories. And from there, we divided up the final time into bins, but depending on how many revolutions the final body is taken, that gives us that allows us to categorize the trajectory into different families. We have the initial B infinity constrained Lambert base build solver that uses geometry and fast, robust, and non-iterative Lambert solver developed by Dr. Russell to allow us to get closed trajectory in a much faster fashion. And yeah, so we have the ballistic trajectory solver that anchors our searches to the low delta V trajectories, and that also allows us to bin all the solutions into families. And finally, we have the half-rep and full-rep trajectory solver that gives us the remaining trajectories. Additional info: the Scout uses a zero radius sphere of influence model, and it also uses real firmware data, which is consistent with how it's being done in industry right now. And Scout also uses normalization of the system so that the algorithm different to what system you're doing. So it could be around Saturn, Jupiter, or even the sun. So just as an example, I did a test with the Callisto Ganymede Jupiter system. I start with Callisto with the arbitrary V infinity vector, and those are my search parameters. It was able to generate all of these trajectories within like almost near like less than a half a second. But this is asking Scout to return every trajectory. If I add filters that we know in advance. So for instance, we know that trajectory, the maneuvers will be more efficient if it happens in the first revolution. We also know that if the spacecraft has a bigger orbit than the body, we have it's more efficient if we have the maneuver at the apoapse. So if we apply those filters, we can actually get basically the same diversity of trajectory, but we can get it in a quarter to a third of the time. And this is just to show you kind of what the solution space looks like. This is plotted in the lat long for the rival B infinity. You have the in-plane solutions, you have the out-of-plane solutions. And here it's plotted in the final time and the pump angle. You can see all the different families. And here's now it's been with the delta V. So you can see they're all within a very low delta V range. So next, I'm going to talk about the medium fidelity builds. As we mentioned, it's typical to plan the tour in the Keplerian model because it allows you to get fast solutions. But one of the problem is that once you take that solution and put it into the high fidelity model, there's going to be a discontinuity in the trajectory because of all the perturbations. And when you have too many of them chained together, that cumulative error means the trajectory becomes infeasible in the high fidelity. And so our objective here is to create an intermediate step between the Keplerian and the full model that reduces the discontinuity errors, thus improving the convergence rate without adding significant computational time. So this is our scheme for the medium fidelity builds. So as before, we're going to use Scout to get a build from the initial condition. Then we're going to do a conversion between build to a medium fidelity build. I'm going to call it N build from now on. So we repeat that process until we have a full tour that is in the N builds. Then we can send that to the optimizer instead. For the medium fidelity model, so in the full model, we usually consider the center body's zonal harmonics. We consider the gravitational pull from the sun. We also consider those from the moons. But because the pull from the moons are usually much smaller than the other two, and here we only consider the sun and the zonal harmonics as our perturbation. And for the sun position, because calling the ephemeris is a very time-consuming process, we instead take a few sample points along the along the sun's position and do a polynomial fit with it, so that when we are doing numerical integrations, we are simply doing a polynomial evaluation rather than an ephemeris call. I have the time span of the curve fit a little bit longer than the trajectory time span because one, I want to make sure that if my trajectory goes a little longer, I still have all the data, and two, I want to avoid the curve fitting artifacts that usually happen at the end of the domains. For the Vilt problem formulation, I have these. These are the parameters that define a full Vilt, and in my code, I set my initial time to constant. I make sure I can let the flyby with the first body move in direction. I allow the maneuver time, maneuver delta V, and the final time to change all they want. But I put a constraint on the arrival V infinity magnitude just so that the quality of the tour doesn't change. And I also make sure the final position match. As a test, I generated random initial conditions and I generated random builds from it. I convert them to n builds and I propagate the trajectory in the full model and see what are the errors I get after. I did it for 500 times and here's the result. So as you can see, each point represents a build and n build pair. The runtime is somewhere between 2 to 15 seconds for each, and the errors, as you can see, kind of goes down by about 3 orders of magnitude. Lastly, there's the Odyssey, which is a high fidelity optimizer, which is developed by Dr. Russell. I'll just quickly talk about it. It uses SNOP as an optimizer in the background, and these are some of the techniques that was used to facilitate the convergence of the solution. So as an example, I planned a tour to Enceladus. Here are my sort of initial condition. I assume an entry v infinity of 5 kilometers per second into the Saturn system. Did a Saturn orbit insertion around that parachrome, which is between the ring and the body, and a 280-day transfer to Titan and doing a parachrome raising maneuver at the apochrome. That gives me the delta V for orbit insertion and then parallax raising to be those, and that is my V infinity. And from there, I use the same process I mentioned before. And here is the tour. I was able to get to an Enceladus orbit, a 100-kilometer orbit around Enceladus at only a delta V of 1.97. As comparison, if you do a direct Enceladus orbit insertion, that's 5 kilometers per second, and the decadal study used about 2.3. And here is the trajectory. Zoom in a little bit to see what's happening near Saturn. These are the maneuvers and the flyby around Titan. Those of Rhea, those of Downey, those of Tethys, and those of Enceladus. Yeah, so to recap, Flyby Tours makes the mission to the small planetary moons feasible. And in this presentation, we've presented the tools that are developed for the moon tour design, and I presented the Enceladus tour. Thank you.
Any questions?
Yes.
This is super cool. So I was wondering, you said there's different parameters you can use to kind of do your search. I was wondering if you included time of flight in that search parameter, because I think I saw very briefly in that final one, the time of flight was like, it was like 2.5 years.
About, yes.
Yeah. And so one of the issues we have with these like outer space missions is time, how long we can go before we run out of energy. Or we have big solar panels, which are really costly.
Right.
And so a lot of like the RTGs have like a lifetime of like 16 years. And so is there a way that we could also, you could incorporate a time of flight optimizer, so that way you're not going over your like energy bounds?
That is definitely something that can be added to the optimizer. Right now, we were only focusing on delta V.
Okay.
Uh,
Super cool.
From online, Can you say anything about how your approach is similar to or different from what JPL's Team X does when they design tours like this? What steps or techniques are they missing?
So some of the things I've seen before is that when they're designing the tour, they went straight to that medium fidelity. But then that means they can't search for a bigger range of trajectories. They like the calculation of that in and of itself would have taken some time.
John, I might be able to add a few
Okay.
comments. So I'd say like a decade ago or maybe longer, these types of missions were considered to be prohibitively too expensive to get to, or they just would be flagship quality budgets essentially, and it would just be too expensive. But there were a handful of researchers, some actually at JPL, and I participated in a few of these teams where we wrote a few papers to sort of demonstrate you could do this if you sort of swap time of flight for propulsion. And there's a few clever tricks, and so those folks are still working at JPL, and there's another couple of teams around the country as well that are putting together similar softwares. So the short answer is it's quite similar, but it all kind of came from the same place, I would say. And what we're trying to do is automate the process. I think Chun mentioned it, but the process is so long and these trajectories are so complex, it's very hard to optimize them. So you wind up doing sort of a point design, and then you're by that time you have to turn in the proposal. And so we're hoping to just automate it to try to get squeeze as much sort of juice out of the lemon.
All right, so if you start taking yours down, so we can start to transition to the other student. I got a couple questions for you, but I know where to find you.